Okay. Yeah. How many people do we have here? 2, 4, 6, 7, 10, 12, 13. So I'm counting on 15 next time. Right? So stay with us. The title of the talk is probably a bit, so who understands the title of the talk? Because it's something that is an ongoing topic in mechanisms and robotics. And what's all about is, of course, about modeling, right? So this is what we are talking about. We talk about modeling of mechanical systems, and in particular about robotic systems, okay? Now the thing is that you all have probably some idea how to model mechanical systems, right? So, good. And there's something that is called modern robotics. Whatever that means is more like a selling point, but anyway, there is some new development that has been going on for at least 2 decades now, or let's say 1.5 decades. And what this is, the new part of it is this kind of, it's this screw theory. So everybody knows a screw, right? Like a screwdriver. Okay, and there's a theory that is called like this. Of course, it's not about screwdrivers, right? It's a bit more behind it. And what the mathematical foundation is called Lie groups. By the way, it's Lie and not lie. We don't lie here. I mean, at least not you. I might lie, but so lie. Lie. It was a Norwegian mathematician actually. It was called Sophus Lie. So if you look up the mathematical, if you just go online and search for Sophus Lie, you will find an endless literature on whatever, because this is one of the foundations of modern mathematics, right? And it turns out that actually this kind of approach is actually relevant for what we do in mechanics. It's not complicated. Like, you can make it complicated. We don't make it complicated, but it's a powerful tool that helps us to do something we have to do in a way that is not giving you the headache that you normally have. And before starting, I would like to know who I'm talking to. So you are from mechanical engineering, right? Who not? Okay, what are you doing if you're not listening here? So you're from?
I'm from electrical engineering.
For what?
Electrical engineering department.
Oh yeah, okay, yeah. Anyone else from somewhere? Computer science?
Electrical engineering.
At least you are doing something good.
Control and industrial automation.
So who has somehow, you know, worked on robotics, like modeling manipulators, like robots, industrial robots? You did, right? Did you? Anyone did modeling robotic systems? So I know you know these famous DH parameters.
Yeah.
Okay. Do you like them?
Yeah, so far.
Okay, that's the one answer. You don't like them.
Yeah.
No, because they are quite complicated, right?
Yeah.
And this kind of theory is supposedly much easier to do, and I believe it is. You just have to know it. So before actually going to see what that is all about, a bit of introduction where I come from and what we are doing, at least roughly. So where we are, maybe here. So we are here. Okay, so zoom out. Then this is that's Europe apparently. This is Russia. This is you are somewhere here, somewhere just not see. And we are here. This is Germany. This is Austria. This is Spain, and so on. So this is where we are, and we are in the which part are we? We are in this part here. We are actually in this part, just between Germany and the Czech Republic. And the university is called the Johannes Kepler University Linz. Doesn't say here. So JKU stands. So I'm not used to this. So JKU stands for Johannes Kepler University. You know Kepler?
Yes.
Yes, it's the guy with the stars and the planets and so on. Okay. So anyway, so the structure maybe is interesting for you. It's a bit different than you're used to, maybe. I mean, every country has different structures. So we have the university as such, right? Then we have faculties. There's the faculty for some medicine. Then we have social sciences and law. And then we have the natural sciences. So this is the faculty. And within the faculty, we have different departments, okay? And we are part of the department of mechatronics. So mechatronics is another word that you hopefully have a bit of understanding about. Because these days everybody talks about mechatronics, and mechatronics is part of robotics, and then people talk about AI. So what's the difference? And in my opinion, this is all kind of a big spectrum, because what is robotics without mechanical engineering? What is robotics without computer science? What is computer science without AI? Right? You know, artificial intelligence. It's all this hype because it all is contributing to some overall kind of purpose, and which is developing good stuff, I guess. So anyway, so Department of Mechatronics. And within each of the departments, you have institutes. So the institutes are the smallest entities, so to say. And I'm chairing the Institute of Robotics. So we have 16 chairs, we have a couple of government partners. The funding is maybe a bit different because we have, of course, we have government-funded research projects, so purely government-funded. Might be good or not, yeah. If you get it, you're happy. But it's a limited kind of budget, right? So then we have, so to say, 50% funded government-funded industry projects. If you're familiar with this, for example, Fraunhofer, Germany idea, so you have companies and universities, and they have ideas, and they make proposals in certain topics, and then the government funds 50% of the budget. And we have a big center which is called Linz Center of Mechatronics. Unfortunately, it's running out. This Linz Center of Mechatronics. It was a 50 million euro project which is coming to an end. Anyway, and if you visit us, we have 5 of these spaceships here. So we have a campus and we have the science park, and we are actually in the science park. So if you have the chance to come, then you will see us. Okay, yeah, I guess this was about it. And what are we doing? If you go online and look for robotics, Institute of Robotics, right? What you mostly find is that most of the statistically, most of the robotics institutes are within computer science, right? I mean, this is so. Now, what is a robot without embodiment, without mechanics? Nothing, right? So, what I'm saying is that there's a big bunch of people out there that just program stuff, and then they assume it works. Fortunately or unfortunately, I don't know, maybe fortunately, it's not a way like this. You have to understand the mechanical system behind it. You have to understand the robotic or mechatronic system before you do any programming. Of course, you have to do, I mean, when you do the programming, you have to take into account the model, the mechanics, but it's the other way around is also, I mean, the other way is also true. When you design your system, you should design it in such a way that you can easily program it, for example. So there's one kind of, closed loop in here. So, and we are coming from, let's say, the mechanical part of robotics. So we start from a decent modeling, and then we do control and planning and optimization by using model-based approaches. Of course, we are living in the 21st century, and model-based is something that people like, I don't know, but there's this idea of just using black box, right? Like AI. You have a black box and you have a network and that learns something. That's not going to be like this. I mean, maybe it's possible in one day when we have quantum computer, but this is certainly not what you want to do. Because you know, you have a lot of understanding about the physical system behind it, right? And you should use this. And this is what we still advocate, and of course we complement it with machine learning approaches. Anyway, that's what we're doing. So it's called multi-body dynamics. Multi-body dynamics is the dynamics of a system consisting of many parts, so to say. Multi-body dynamics, so you have multiple components and they are somehow interacting, and this makes a whatever kind of mechatronic system. And many things, and then we optimize it. I mean, first of all, we optimize the system, but most of the time the system is given. Like you have, for example, our industrial partners, right? They have robots. Some of them are manufacturers of robots, so the system is there. Now the question is, how do you control it such that it's optimal, in a sense it's energy optimal, energy most efficient, it's time optimal, you want to do whatever you have to do in a short period of time, and also what is minimizing fatigue and so on, right? So the lifetime and so on. This is all what's about the optimization. And then optimization and control goes hand in hand, right? Because you optimize it so that you can control it, and also you want to control it so that it's becoming optimal. And all this leads from the decent model to an implementation in the end. That's the tricky part. And I guess the lecture is going to be in this direction. How to get models in a way that they are efficient. And efficiency has two kind of aspects. I mean, first of all, it should be computationally efficient. Whatever you have there should be, in the end, somehow running on a real-time system on some computer, right? Okay, but efficiency also has to do with how easy can you get the model. I mean, is it very difficult to make it for you as a programmer or so? So, and there's a balance between, and this is where we are working on. Okay. No, this is one way. This way. Yeah. So systems. I don't know. I guess you know many of these systems. Industrial robotic systems. I guess this is what you know, right? So this is a robotic arm. They call it a serial kinematic chain. So it's this case is a 60-wheel freedom system. Here we have a it's also 60-wheel freedom system, but also we have 7 degrees of freedom system. And then we have, of course, humanoids. Right? This is our own humanoids. Of course, it doesn't look like the one from Boston Dynamics or any kind of these fancy systems. But anyway, it's our own and it's working. So it's not. This is not really what we are aiming at. It's just for students, but very interesting topic. Then we work a bit on this. Yeah, what could it be? It's like an exoskeleton, like a lower limb support device, right? Because for many reasons, either you have a sickness or you get injured or so, you need assistance. And also we are living in an age of, well, let's say our population is getting older, right? And more people are needed to support elderly people, and of course we have a shortage of this. And this is why we are interested in maybe low-cost support devices, assisted devices for humans. Okay. And then, of course, is this mobile manipulation topic, right? So you have in the modern manufacturing industry or in other contexts, what you have is, of course, a robot. It's not good to see here, but anyway, you have this, again, you have a kind of a repeated structure of a robot, right? Like a robotic manipulator. And you mount this on a mobile platform. So what you have here is a mobile platform that can go all around, okay? And you know this, right? Because this is the omniwheels, for example. And so essentially you have a mobile platform that can go around. This is like what's used in logistics, like indoor logistics, right? These systems, they go in the factory and autonomously and so on. But now the idea is to have an arm on top of it, like a robotic arm, right? To do some manipulation tasks and so on. And actually we have also this kind of thing. And what you have to do is you have to first, if you want to really optimize it and control it in a good way, then you have to understand the system before. And that's what we're doing here. So this is our prototype many years ago. It's an old video. Anyway, so this is how it works, and then you put this arm on top of it, and then you have a mobile robotic system. Okay. Of course, it's all easy said, but not easy done, right? So it was a bit of bit of work to do to get the arm on top of it and so on. But anyway, it works. Now, if you look at these robots, for example, we have 2 robots here. Of course, they're industrial robots, right? They're just Comau, it's an Italian company, but anyway. So we have 2 of them, okay? And what you see here is what you cannot do with an industrial controller. What I'm saying is that they are operating with the speed. They're operating with a speed that is not possible when you just use the. Okay, go back and forth, that is. Yeah, I'm just looking here because I see the screen there. Yeah, so what you see here is an operation that you cannot do with just using the standard controller, right? For many reasons, and one reason is that you wouldn't be able actually to move them as fast as possible without actually going into the immersion system. This is why you need a model-based controller. So we have a model-based feed forward that is somehow helping you. I'm not sure if you come to this point in the lecture. And also what is important is that they are, yeah, and what is important, I'm just finished, the second point is that they are actually avoiding collisions. And that is something that is not easy. So we have 2 robots, they are semi-independently operating, and we are avoiding collisions in real time. So this is also something that is not easy. Okay, other applications is where without models you wouldn't be able to do it, is lifting of objects. This sounds pretty simple, right? So what happens here is that you have 2 robots, and they are lifting an object here. Oops, this is so fast. Exactly, this is the object they are lifting. And by the way, that object here would be too heavy for each of them, right? But together they can do this. And this is called collaborative robotic manipulation. And if you think a bit what you have to do in order to get it up and running, that's not easy. Because first of all, again, this is with the maximum speed that you can do. But anyway, you cannot do this with standard industrial control. What you have to have is a model, and you have to have a good control scheme behind it. It doesn't repeat automatically, so I have to repeat it. So what's the problem here? So what would be, okay, what are limitations of an industrial robot? What's, for example, the accuracy? So how precise can you position the end effector? Huh? So the end effector is this, like the end, the flange here. So how accurate? If you control a robot, what is the precision with which you can reach a point? What do you think? Is it a millimeter? Is it a tenth of a millimeter? What is it?
Millimeter?
Yeah, it's if you just buy it off the shelf, it could be a millimeter range. And that of course is not healthy, because if it would be millimeter, like plus minus here and plus minus there, this would slip, right? So what you have to do is, and this is why you see actually these blue boxes, these blue elements here. These are force torque measurement devices. Okay. So what you do here is a kind of a real-time, they call it admittance control. Essentially, you control a force, but essentially you control a kind of elastic behavior. Okay. And that's what you have to do. And that is possible. I mean, this is not new per se, but what is new is to do it with this speed, because this is real time. So this is also something just to motivate you, because without the model this would not be possible. Okay, so let's go to the boring part of the lecture. It's all about mechanics. It's all about mechanisms. And what we are interested in is analyzing systems. And in particular, systems possibly with a closed loop, closed kinematic loops. Okay, so just to get you all on track, what we're talking about, we talk about these kind of systems here, right? They are moving, okay? And they are, so when we say closed loop, apparently they have like, so this is a 4-bar mechanism, like this typical, 4-bar crank mechanism. So you can say there's an input, sorry, this was too much. This one is enough. Okay. What you can say is there's an input, maybe this crank turning would be the input, and the output would be somewhere here, I don't know. So it's a kind of input-output device, right? So a mechanical device that has an input and an output. I don't know if this makes sense here, if this is an input-output device. Anyway, it's a mechanism. And there are different things. Okay, something like that. There are different things to consider. First of all, when you make a model, or when you design it, you need to you need to estimate what's the mobility. I mean, how do I know what the mobility of the system is? What I'm saying is, what's the degree of freedom? On the other point, asking, how many inputs do I need, right? I mean, here it's seemingly clear, because yes, one crank, and then if you turn the crank, then the system is moving. What about this one here? What's the degree of freedom of that system? I mean, I hope you understand what it says here. This is a revolute joint, and here 4 revolute joints, okay? Here we have 4 revolute joints, and there is an intersection. I mean, so for this special mechanism, the axis of the joints, of the 4 revolute joints, are intersecting permanently. Okay, this is why it's called a spherical mechanism. As a consequence, what happens is the 4 bars, I mean the yellow thing, they are moving on a sphere, and the center of the sphere is here. Okay, but that is also a condition, because otherwise, if this would not be the case that they're intersecting, then it would not be mobile. Okay, it would be rigid. It would be a structure, right? If you are in civil engineering, this is good for you, because then this would be purely a static system. Pretty boring to us, because you want to have it moving. Okay, so what's the connection between the two? Is there any? But they have 4 joints, right? They have 4 other joints. Okay, is there any other similarity? Maybe?
4 linkage.
Huh?
Both have 4 linkages.
Both have
Link. 4 linkages.
Yep, right. What about the geometry?
One linkage fixed.
Yeah, one link. No, it doesn't have to be. They can be free floating. They don't care. I mean, this mechanism doesn't care if it's fixed or not. So what we come to this in a minute. Actually, what you're describing is what we call the topology. Because what you're saying is we have so many links, we have so many joints. That's fine, but I can close my eyes and then just throw the links to the joints and I get something. but they are not just something, they are very special. So what's the particularity? Why is this moving here? Because the axes of the joints are all parallel, right? Otherwise it would not. And as a consequence, all the bodies, maybe this is fixed, maybe not, they're moving in the plane, okay? Okay. And I was saying these four links, they're moving on a sphere, okay? The similarity is that that for all of these, for both mechanisms, all joint axes are intersecting one point. Here they intersect at this point, and just imagine you take this to infinity. So what happens if you go to infinity? Well, you are here, right? So this is just a projective equivalence. So they're essentially the same, just someone, assembled them in a different way, but they're all such by the same conditions. Okay, then you can combine them to some funny mechanisms, and let's look at this one here. This is maybe an example of what we call a robot, and in particular one that is called a parallel kinematic robot. I think this is something that is here, and we call this PKM. So PKM always stands for parallel kinematic machine or mechanism, and PKM is just sort of the same. So okay, what's particular about this one? So essentially, if you are in this area, this is the Singh mechanism that goes back to different authors at the same time, by the way. And you can say this is the platform. So there is a platform that is to be positioned, right? And if you analyze it, you will see the platform can only translate in space. It cannot rotate. Okay? That's important. Number one. So this could be the output. Let's say this is the output. You can put something on this. You can sit on it, or I don't know what you can do. And the inputs are the linear actuators, like the sliders here. So these are the inputs, right? If you have motors there, then you need 3 motors. And this is an interesting mechanism, because you have, let's say, Cartesian inputs like linear actuators, or let's say translational actuators, no regular joints, right? It's all translations. And what comes out is again translations. You have 3 independent translations, and you have 3 independent input translations. And in between you have some mechanism that does whatever it does. Okay? Okay, good. Wonderful. More mechanisms. If this humanoid that I showed at the beginning, normally or many times people want to have humanoids even resembling resembling human in the sense that they have also hands, right? Like robotic hands. The question is, if you need it, that's a different point. But many times, so if you go into the market, if you look at, if you want to buy one, you get one normally with 4 fingers, 3 fingers or 4 fingers, okay? And there is, just say, this was Professor John Dye from King's College London. He designed this kind of this hand. Does it say somewhere? Oh yeah, metamorphic hand. In a sense, so metamorphic in a sense that it can change its mobility. So what I'm talking about is, for example, if you look at, do we have it here? We don't have it. So if you look at this palm, so the palm actually is made of, it's not easy to see, I guess. So the palm actually is again a closed loop mechanism. It's a 5-bar mechanism. So you have 5 double joints. Yeah, maybe it's not easy to see, but what the system can do is, so your palm, look at your palm, right? So, and imagine that your palm, that you could not do like this. So it would always be like one rigid body, and try to do something sensible without actually without deforming your palm. This is impossible, right? But this is what you have when you buy these 3 or 4 finger robotic hands that are on the market. They always have 4 fingers fixed to something called the palm. And this is, of course, not really helping, but if you want to grab something, and that's why they had this invention. So that's it. And it's metamorphic because you can somehow, turn it and then it becomes again a rigid. Anyway, so anyway, what I'm saying is that there's lots of topology, different topology out there. Maybe I'll skip this one. Yeah. Or maybe I'll just show it. But this is just an I don't know why I put it in here. There are other systems, free-floating systems. You mentioned that this is rigid, so this is fixed, the 4-bar was fixed. Not necessarily. And there's one thing that, of course, happens in reality if you go to space, for example, right? And there's this, there are many reasons there's a big need actually for stabilizing satellites, or for stabilizing what we call robotic, space robots. What is a space robot? A space robot, I know the picture is absolute nonsense. I've better, but anyway, this is a video. So let's say this is a satellite, and on the satellite is again a robotic arm, right? And this is in space. So, okay, it's nice, but why do you need it? For many purposes, for example, for maintenance, right? Because there's so many satellites. I mean, if you go online again and search for, there's a nice chart. Well, not nice, it's a terrible chart actually. You see all these satellites and you see the debris. And that's a big danger, right? Because that, if nothing else, this is going to be a very big problem for communications and for everything for the future. Anyway, so what you have to do is you have to somehow get all this debris out of space. And there's big and small debris, right? And there are satellites. And in the old days, the satellites, if it's not working, just leave it there. That's not working. It's not allowed anymore. You have to somehow get it. And that's the basic idea. So you have a, so to say, a servicer, like a satellite, with an arm on top, like a robotic arm, and then you catch whatever you have to catch. Like another satellite, you take it in, you do some repair, and that's when you get it out. What happens if you're in space and if you're catching something? You start to tumble, right? Because you have momentum influx, and that's what you have to cope with. And this is what we did, and I'm not sure if this makes any sense to present, but anyway, it was in the slide. Okay, good. What's this doing? Let's start with, let's proceed here. Yeah, okay, I was actually alluding to PKM, as we call it, purely kinematic machines or manipulators. So all of these, or maybe a bit of a history, I don't know, when did robotics start? I don't know when robotics started. But I guess the kind of first robotic manipulator was in the late, or the early 70s, right, 1970s. So they started with this. And again, they call it robotic arm because it simply resembles your arm, right? You have 6 or 7 joints, or maybe 3 or 4, depends on what you do. And this is always a kinematic chain, like an open kinematic chain, right? So, and then it was in the late 90s actually. So, and they started with introducing robots with closed loops, like the one I've been showing here. This one, for example, this is an outcome of the development that started in the late 1990s, okay? And the difference to, of course, this robotic arm, I mean, yeah, these ones here, for example, as I was saying, they are just an open chain, right? So there's one link after the other and that's it. There's the empty effect. Here it's different, because here what you have is there are multiple chains actually connecting the platform. Okay, this is a big difference from the modeling point and from the control point, and so on. So, and this is what we are maybe have to look at first. So, in mechanisms in general, sorry, I'm not yet used to this one. In mechanisms in general, we are always using this kind of closed loop systems. So we always have mechanisms for one or the other reason. I mean, if you look in your car, if you look in your, I don't know, daily life, there are so many closed loop mechanisms. You may not even realize this, but there are so many closed loop mechanisms. So this is a kind of a standard practice since ever. But in robotics, this is a bit of a new development. And yeah, and we have to say what the difference is. And I was actually saying that, a PKM, a PKM is a purely kinematic machine, is a special closed loop mechanism in a sense that we have a moving platform. And again, this is a different one. Maybe this is one of the oldest one that was proposed. It's called the Gov-Stewart platform, or simply called hexapod sometimes. So hexa means 6, right? Pod means, who can speak Greek? It means leg actually. And the hexapod is something with 6 legs. By the way, this comes from, mostly this is a term from biology. Hexapods are insects, right? Okay. Anyway, so and just go to the platform, because what you have here is a platform, and then you have 6, 1, 2, 3, 4, 5, 6. Well, they call it legs. They're not legs, that's not walking, but anyway, they call it legs or strut or limb or something. Yeah, so and this is the kind of ingredient for a PKM. So you have a moving platform. So there's a moving platform, and it's connected to they call it the fixed platform. Platform and ground, I would call it, because normally this is supposed to be somewhere stationary on the ground. So this is the fixed platform, this is the moving platform. Essentially, it's a moving platform that is connected to the ground. And because here in this case, what you have is like spindle or something, so you can actually change the length of these legs, these struts. Okay, spindle drives or something, and yeah, and that's it. Because so what is it then? We have here universal joint. So what is universal joint or hook joint?
Yes.
Like combination of two rubber joints. Okay, and then you have here the piston. So this is kind of a linear joint or prismatic joint, like just pure translation. And then you have this spherical joint here, like a ball socket joint. Okay, wonderful. Yeah, what else? Yeah. Good. And why did people actually look into this? Why did anyone invent this? Simply because, what's the first one? Stiffness, for example. But essentially, what is it? If you, again, compare it to this robotic arm, I mean the standard robotic arm, where you have one link after the other, like the ones here, like here, here, for example. So what is it then? Imagine that you push at the end effector, right? So there's certain, I mean everything is, I mean nothing is rigid in reality, so that's for sure. So when you push at the end effector, for example, you can measure some deflection, okay? So what's the cause for what is the reason for the deflection, for this evasive motion? Well, simply some stiffness, right? And what happens in this standard robotic arm is that you are kind of adding up the stiffnesses, right? You have, I don't know where it starts, I don't know, you have the stiffness of this gear, then there's one here, I guess, and there's one here, and so on. And you all add them up in a long chain, right? And then this all together gives you the total stiffness. And also what happens is, look at this motor here. So there's one motor, right? That is, moving the system. And it's actually moving all the motors that come after this motor in the chain, right? And the same is here. So this motor is not actually directly, influencing the end effector motion, but it has to move the whole system for no purpose actually, because I don't want, initially I don't want to move the robot, I want to move the end effector, right? So what I'm saying is, this was actually one of the arguments for having these PKMs, because the stiffness and the payload is increased. Because what you have essentially is, you have one platform, and you are supposed, I mean, the aim is to move this platform, okay? And to generate, for example, a force and a wrench, a torque and a force at the end effector, at the platform. So you have one actuation system that is actually acting on the platform. And then in parallel you have another one. So actually what happens, you add up all these forces. And on the other hand, you have one of these struts with a certain stiffness, right? I mean, there's a gear here, I don't know, some joints, and there's some stiffness. Of course, the stiffness is much lower than in the robotic arm. But what you do here, you kind of combine them in parallel, right? And whenever you have springs in parallel, what happens is it becomes different. It's very simple, right? So in the end, what you have here is a much stiffer system with much higher payload, and of course, because you have the motors all acting together in parallel, it's not like that this motor has to move this motor and so on, and then eventually it moves the platform. No, here they're all acting at the same time in parallel at the platform. So you're actually adding forces, you're adding stiffness, and you're adding payload. So there's no free lunch apparently, right? I mean, this is what you learn in life. So there must be something. And what's the problem here? The problem is, if you look at the workspace, for example, the workspace of this PKM, for example, this dual core platform, looks like this. Okay, the shape is one thing, and the other thing is it's pretty much, it's much smaller than what you have for these standard robots, right? So simply because you can imagine if you move here, then you are kind of colliding here, then you are in the limit of this joint and so on. So in the end, the workspace is limited. So this is a design optimization problem. Because you want to design them such that, of course, you have all these nice features, but at the same time you want to maximize the workspace. So, but anyway, the workspace is smaller. And then we have singularities in the workspace. Not sure if you are familiar with this, but anyway, this is just to let you know. I mean, this usually in the middle of the workspace you have some critical configuration, which are called singularities, and that happens only for PKM. And they are good examples for this. The oldest one, as I was mentioning, is the one from Goch. So Stewart and Goch, they have been at the same time developing it, and that goes back to 47. And essentially, that's the PKM I was showing here. And essentially, what they did, this is a very old photograph, and this was just meant, don't look, this tire manufacturer, and this was a tire tester, right? They wanted to have a system that can push, generate high force, but at the same time is flexible. And that's why they came up with this idea of having, the tires go in here. I don't know what happened here. Anyway, so and then they push from here with the hydraulic cylinder, and that's originally what happened when this came from. And the same idea is used these days. I mean, there are big machines, and even you have a tank on top of it, where you have flight simulator. You can really do flight simulation. If you go in there, you get sick, and then and of course you have hydraulic actuators, and there's a big machine. But at the same time, because of this the stiffness, I mean the high stiffness, it's also good for to resist actually forces that are introduced by some process like milling or stuff like this, and that's why they are used. That's a machine from maybe Ingersoll. I don't know. Many companies are doing this. So essentially, this is the PKM. You see again the hexapod here, and here's the tool, and you do like freeform 5-axis, whatever milling or so. Right? And the good thing is that you can have high forces, but still achieve a good accuracy because of the high stiffness. Okay, perfect. It goes the other way also, like small forces, small workspace, and high precision again. So this, for example, is an hexapod system, the same idea. But what you have here is piezoelectric actuators. So the distance is the change of distance is pretty small. I mean, it is some centimeter only, not that small. And because of the piezoelectric actuators, it's super high accuracy, so it's highly precise. And they are supposed to be used for whatever way you need high precision, for example, brain surgery. Never happened, by the way, in brain surgery. Okay, good. To maybe just sum up this kind of overview, of course, this was a system that, by definition, had 6 degrees of freedom, right? Which is kind of obvious, hopefully, because what you need here is full motion capability, right? You want to have a free translation of space plus spatial orientation, right? And that's why you have 6 inputs. So you have 6 degrees of freedom, and I'm saying 6 degrees of freedom, 3 translations and 3 rotations in space, right? But many times you don't need this, and in particular in manufacturing. I'm not sure if I don't have the video here, but there are many videos out there. For example, for this famous flex picker, right? So the system is called the Delta for historical reason, and there is this from ABB company. There is this flex picker, and you find lots of videos where it is impossibly fast picking objects. So what you have here is it looks a bit different, because the end effector here again can only translate in space, and you have the maybe not easy to see here, but what this is carbon fiber. So very light, slender beads, and they are just actuated by 3 motors. It's not a good picture actually. So there's a motor here. So essentially there's an arm that goes up and down. You see the same here. So there is an arm that goes up and down. So this is always ground fixed. So if this moves, then this point moves, of course, and this point and this point. And what happens is that you're moving actually the end effector up and down and so on. And it's again 3 degrees of freedom translations, but the moving mass is absolutely is very low, right? So the moving mass is very low because you only have to move these slender beads, and if you make them of carbon fiber or whatever, then the load is, I mean the weight is very low, so you can have a high speed, and that's what they do. Okay, good. And there's a development that, and there was a development here that comes from the somehow it's I don't know, the video is apparently not good. So this would be okay, what you see, if you would see it, I mean, for some reason the video is moved up and I started. I don't know. What you see is here. So what we have here is the same idea. So you have the platform, and then you have again, you have a rubber. Hey, come on. So you have a rubber joint here that goes up and down. There's one that goes. So for each of the directions in space, you have one actuator, one linear actuator. Okay, and this is acting on this kinematic chain and on here, and they're connected to the platform. And what happens in the end is, of course, that you can move the platform. But somehow you can't really see this here because it's cut off. Anyway, and then the same group actually in Laval University, Quebec, they came up with a different thing. Or let's say they included one more leg because you have 1, 2, 3, and then they have a fourth one. And the basic idea behind this is to even more increase the payload and reduce the stiffness. And in the end, because the system itself is very light, you have this kind of direct translation from input to output, and you have one more leg actually. You can have a very high acceleration. What you see here is like 4G, 4 times the gravity acceleration, but they already went to 100G. Okay, that was it. Anyway, but you can imagine how this works. Other systems, like the problem with the workspace boundary, I mean with the limited workspace, that remains, right? And some years ago actually, we came up with this idea. So essentially what you have here is, again, like a PKM with 3 degrees of freedom. You have 6 degrees of freedom actually. So this, the end effector here, I mean this is the end effector. It can have free orientation and translation in space. And you have 6 inputs. So when I say 6 inputs, I mean that you have each of these slider can move in a plane. So we have X, Y of each of the sliders. So we have 2 inputs, I mean 2 translations per slider. So we have 6 inputs again. So about the workspace. So the workspace is kind of enlarged, quote unquote, to infinity by having this freedom of moving in the plane, right? So as long as you invest in this planar foundation, you can actually go all along as far as you want. Of course, this is usually with magnetic or air bearing and so on. This is not cheap, but if you need it, you can do this. Okay. Okay, and then finally there's an example for what, so because the question here is, what's the degree of freedom of the system? And that's not easy to say. Because that is an example where the degree of freedom is changing. Now what you see here, for example, is what you call a lockup mode. Because if you look at the platform, it cannot move. But then once it switches, it goes actually through what we call singularity. The platform can move in the space, in the plane. Okay. And that's a planar mode. And you can imagine, now, maybe stop it, what could be the input for the planar motion? Because always the question is, what are the inputs? So is the motor here, or where are the motors? So for the planar motion, and also for at the beginning, like this one, what's the degree of freedom? Well, 3, because you can only turn these, I mean, each of the length. So 3 degrees of freedom. Okay? And what's for the planar mode? It's also 3 degrees of freedom. The only thing is that the motion mode is different. Because the way it can move is different. Here it can move on a plane. So possibly you want this dart or this rubber joint to be actuated. So we should have a motor maybe here. Whereas in the first situation, like here, you might have to turn here because otherwise you're not moving the system. Okay. Anyway, so this is an interesting thing. I don't think it has a practical application, but anyway, it's there. So finally, there are other mechanisms like all of them we call lower mobility mechanisms because they all have degree of freedom less than 6. And there's one that is also coming from Clermont-Ferrand from Laval University. They call it an agile eye. So like an eye, but an agile eye. And essentially it's a pointing device because what you see here is we have one. Not used to this one. We have 1, 2, and I don't know. Yeah, here. That's the other one. So we have 3 motors, right? And they are turning. Again, this is a spherical mechanism. Because if you look what happens here, we have 1 rubber joint, 1 rubber joint, and the other one comes here. So they all intersect again at 1 point. Okay. So whatever they do, they can only turn this let's call it platform. And if you have a pointing device, then this is easily positioned, and also it's very agile because the moving mass is very low, and you can have very high and precise motions. Okay, and eventually what people came up with is having more inputs than outputs. This sounds a bit redundant, and in particular this is actually redundant. It's called redundant actuation, right? So let's say that you have a system of, look at this one for example here. This is from a Chinese university actually, from Tsinghua. What you have here, you have this end effector is only moving in a plane. Maybe this is better. So this is only moving in a plane again, okay? So this means 3 degrees of freedom. This means you need 3 inputs. But they have 4. So they have, essentially they have 2 spindles here, 2 spindles here. So one is moving this end, and that end. So you have 4 inputs. Why? It's just because you have more power, right? And also because you can homogenize the transmission properties. But at the same time, you have to be very careful because if you have more actuators than degrees of freedom, you have to really synchronize them because otherwise they are fighting, they're kind of interfering with each other. And this is a machine that comes from Montpellier in France. The same. So it has 4 degrees of freedom, but it has 1, 2, I don't know, 3, 4, 5, 6 inputs. Okay. This is actually a big behemoth. Actually, this is a big monster, so to say. But they are very strong. I mean, it can be very fast. So the size is really like the height is like this, and this is actually a big. I think it was marble or something, or concrete or something. It was a big stone. Because it's so fast that you have to have a foundation that is withstanding this. Anyway, good. There we go. I think we should maybe get slowly into the mathematical topic. What about this redundancy? What about singularities? Look at the left-hand side. So this would be, again, a mechanism. I mean, it's called a mechanism. There's 2 motors, 1, 2. As input, and what you do, you turn them, and then you're essentially positioning this point in the plane, right? So, I mean, if you look from top, it's more like a 5-pole mechanism, 2 inputs, and then you position that one. What happens at that particular configuration? What is possible here? What is not possible? Okay, what I'm asking is, the motors, the inputs are here, this one and that one. Okay. So question is, can you generate a motion in this direction? No, you can't. No, you can't. Because if you move this one and this one, whatever happens, you only go this way, right? Because they are just aligned. I know it's very simple, but that's a very special case of so-called singularity. So this is what you cannot do. You cannot generate motions in this direction. If you are in a, if this is not aligned, then you can, right? Then you can always. So this is what you cannot do. No, this is what you cannot do. What else can you not do? You cannot withstand the force in this direction. I mean, you can even lock these actuators. I can push here and this flips in this direction, right? What can you do? That's a good question in this case. Okay, anyway, so this is it. To get rid of this, because this is in the middle of the workspace, right? And if you look at the workspace, then this is more or less in the middle of the workspace. And this is the, if you look on top, this is where you have this kind of situation. But if you add one more of these legs, then you get rid of the singularity, and also you homogenize the transmission property. Yeah, there's a measure for measuring it. Anyway, I'm not going into detail. You see that this is, of course, somehow not homogeneous. Here it is much more equally distributed, and that's one other reason for actually introducing redundancy. The last and final version of redundancy is No, this is not redundancy. What was the common kind of denominator for all these systems? I mean, the common denominator, or what's known to all of them, is that we have exactly one single, simple, here. All these legs are just, again, kinematic chains, right? There's one joint, next joint, third joint. There are no closed loops in it. This is normally the case. I mean, normally. So, and what some people did is actually to introduce this kind of systems. And it looks like this, right? So it's moving. So essentially you have 2 degrees of freedom. So 2 degrees of freedom in the sense that the platform can only move in the plane. So it cannot rotate, and it can only move in the plane. As it's here, right? So you have just the X, Y, or whatever the coordinates are, okay? Okay, so 2 inputs. But the difference is, you see again, the two, there's a loop here, right? Because if you look, there's a closed loop here, there's a closed loop here, and again, this is the same here. And by the way, this was already the case for the delta mechanism, because the delta mechanism is one of the first that was introduced with closed loops. Because what you have here is, of course, these struts, they are connected by 4 socket joints, right? So essentially you have, again, the closed loop here, but this is a very special kind of closed loop. Okay, and I think now we should maybe get to some more details. So we talked about loops and not loops and joints and where the joints are. And at the beginning you mentioned so many joints, so many links, but what about the geometry? And we really have to distinguish, or let's say separate. First of all, look at the topology, and then see what particular geometry we are going to give the mechanism. Okay, and if you look at all these mechanisms, there are different topologies, and I don't know why I have this picture. We need to, just for completeness, have a bit of terminology. So, if you look at these systems, I'm sorry, I'm not used to this. If you look at these systems, right, you can always talk of what we call kinematic chains. But what exactly is a kinematic chain? And maybe simply summarized, is a kinematic chain is just a system of links and bodies that are connected by joints. Now the thing is, we have to distinguish by open and closed kinematic chains. So essentially, this is all kinematic chains. These are all kinematic chains, right? So there's one joint, 6 joints here, and then in between the joints we have, they call it links, I would call it bodies. Anyway, they are the switching elements, okay? And the common to them is that we have one link, one joint connecting to the link, and then there is exactly one unique successor for each of the joints and the links, okay? And that's when we have, an so-called, and that's when we have an open kinematic chain. Open means that there's no loop, okay? And closed is, of course, the opposite. A closed kinematic chain has no ends, has no free ends, okay? A nice example, a good old example is maybe the human body, right? If you're on biomechanics, for example, and you want to, or if you are working on, for example, this exoskeletons, right? As I was saying in the beginning, if you want to develop a system that supports a human, then you have to first understand the kinematics of the human body. Now, how do you model a human body? And the interesting thing is the human body is modeled as a multi-body system. Make sense? So the human body is modeled as a multi-body system. So essentially what it means is that multi-body means multi-link, right? So you can actually say, okay, the hand is one, if this is one dimensional system, so the hand is one link, or one body, then comes the lower arm, the upper arm, and in between are links, joints, right? So this is it. But of course, technical joints, not biological joints, because a biological joint is completely different from a technical joint. Anyway, so, and this is a nice example for topology, because if you look at which one then, I don't know, the free-floating human body, for example, right? So if you look at this mannequin here, so this is, of course, a kinematic chain, right? It has no closed loops, because the human body does not have closed loops, if you are not fixing it to the ground. But what you can say, it has what we call a tree structure. So a tree structure, in a sense, that you can, for example, take the hip as the root of a tree. So you take the hip as the root of a tree, and then you say, out of this root, or let's say the hip, to emanate all the chains, the kinematic chains they are actually getting out of this root, right? Yeah. And this brings us to some further definition. Okay, because so what I'm after now is the topology. So this was this. So we talked about a kinematic chain and an open kinematic chain. An open kinematic chain has no closed loop. What about systems with closed loops? There are special systems with closed loops, and these are what we talked about, the PKM. So a kind of kinematic manipulator or machine, sometimes called a machine, it's just a mechanism where the mobile platform, this was the one here, so for example this one, is connected to the ground by at least 2 kinematic chains, and there are no further kinematic chains. So it's not like that there's some chain sticking out here. So essentially platform, ground, and the platform is connected to the ground by certain kinematic chain. Okay, and this of course has kinematic closed loops, but this is a very special closed loop mechanism. Okay, how do we represent it now finally? How do we represent it? First of all, I would like to say, why don't we number the bodies, or the links, right? So I would start, I don't know where I start, but I know where I start. So the ground, because we are talking about stationary system, so the ground, I always give the number 0, right? So we number the bodies, and there's one body I'm not interested in, but I have to somehow number it, which is the ground, because the ground's not moving, I don't care, for the time being at least. And this gives number 0. So this gives number 0, ground is number 0, and the rounded numbers, these are the bodies. So number 1, 2, and you can count, I guess. And apparently we have 10 bodies here, yes. And number 10 is the platform, okay? And good. What about joints? Then I number the joints. I mean, I don't have to explain, I guess. So the number the joints, number 1, 2, 3, 4, and so on. Okay. Very nice. So now imagine you want to write a computer program for simulating multiple systems, or for simulating robots. What data structure would you actually use to represent the topology? Because somehow you have to store data of your system, okay? So what data would it be? It would be, eventually it will be the geometry of each of the bodies, the mass, the inertia, whatever you need. But before you do this, you have to have a certain storage, right? A certain data structure where you put all this data in. So which one, so good question, right? And essentially, I'm too fast, sorry. Forget about it. So, and there's a very good data structure, and there's a very good mathematical concept, which is just a linear graph. So a graph is very simple. I mean, there's lots of theory of graphs, but it's not for us here. A graph to us is just, a set of vertices and edges. And the vertices, there's the right pointer here. So the vertices are our bodies. Okay, so we have number 0, of course, the ground, and then we have whatever. So look at here, we have the ground, number 0 here. Then we have number 2, 1, 2, 3, and then 10. Okay, there's number 2. 1, 2, 3, and then 10. Okay, so I just I place the graph such that it makes a bit of sense. Okay, so and in between the bodies are, well, let's say the bodies are connected by joints. Okay? And in between the vertices are the edges. Okay, so the edges are representing the joints. So I know exactly which body, whatever body number you have, is connected to what other body by what joint. Okay, so now in your data structure you will have a graph. So each of the vertices represent your body, and then you would say, okay, this has 6 kilogram, and this has such an inertia and such geometry, and so on and so on. In this data structure, and that's good. So and then you have the edges in between. Okay, then the edges, what kind of properties do they get? Well, they get certainly the type of the joint. For example, saying one is, what is one? One is a prismatic joint, like a pure translational joint. Number 2, for example, you would say, this is a Rappler joint, and so on. By the way, do you use no, I'm tired. Like C++ or something, like object-oriented programming or so? Because then you would have like a class, right? So you would have a class joint, you would have a class body, you would have, I don't know what. And each of these classes has members, and the member is like all these properties, and so on. And you have methods, right? For example, one method is, for example, for the joint is to say move or something like this, or and so on. We will see this. Right. Okay, that's it. It's not much to say much. What's this? Yeah. Then of course we have these systems, and what's this? So then we have different numberings. And by the way, you can. I use this this Arabic numbers, but you can also use Roman numbers. You can also have like pictures. I mean, it's up to you what you put in the how you call the edges and vertices, right? You can call it the Mickey Mouse or Hollywood or I don't know what. So, and that's up to you. Now the question is, given this system here, come on, move. So given this system, how does the graph look like? Well, I've shown it already, right? But the graph is probably unique because once you have numbered the edges and vertices, this is the graph. Okay. Okay. What you see is, or what you have been seeing already, probably, is that there are closed loop in it. I mean, there are loops in the graph, which correspond to kinematic loops in our mechanism. Because now you're working on the graph, right? But don't forget, this is a kinematic. This is a topological graph. It has to do with kinematics. Okay, so now we see that there are loops in the graph. The question is, how many loops do we have? Well, you see probably 2, right? And I put them number 1, number 2. Some people put them differently. It doesn't matter. Now the question is, do we really know how many loops we have here? Can I have more loops? Now, if you have your data structure, your class, call it graph, your class graph, will have a method, and the method says something like give me loops or compute loops. How many loops do you have to compute for this thing? Well, I have 2 here. Can we have 3?
3.
Wonderful. Can we have 4? Okay, you can have it. Yeah, we can maybe have. I don't know. Okay, I'll repeat my question. Can we have more independent loops? I mean, the answer was correct when I said, can we have more loops? Yes, you can. Now my question is, can we have more independent loops? But you shouldn't answer me. You shouldn't say, hey, what do you mean? What does independence mean? I don't know. We don't have time for that. Who's in electrical engineering? You have been. Okay, so you know about the circuits, right? This is like a network. And then you know, I guess you do, how to reduce how to introduce like fundamental, how do you call this, loop currents, right? You know how? Huh? What? I'm not sure how you call it. Yeah, I guess that's what you call it. Yeah, yeah. So it's like a, let's say this is an electrical network. So you have certain elements in here. So you can reduce. No, what is that? You can. What's the name in English of this? When you. So let's say there's a current here, right? So this current can be represented as the sum of the current in this loop and this loop.
Yes.
And how is this procedure of finding the loop called? Okay. At least you know hopefully what she's saying, because I don't. No, I know what you mean, but I have no idea this term. Yeah, yeah. So essentially it's the same. And there is apparently, how do you find these loops? Because this is the same question. How many independent currents can you find? How many independent loops can you find? And that method is the same.
It must identify nodes.
Yeah, yeah. So anyway, how you do it? So you know how to do it, and it's the same procedure. So you find independent loops. But the good news is, if you implement this, your class will have already this function, right? Because in most of these languages, you have data structure that's called graph, and it has the method find loops. Okay, good question. I would say you only have two independent loops here. Because you can have, for example, this one, but the, so to say, current of that loop can be already represented by the two loops here. So they are not, this is not independent. Okay, because we talk about currents now, electrical currents, this is not an electrical network. What would be the counter, or let's say the equivalent for the current here? So what was the edge? That was a joint, right, in our case. What is normally in electrical engineering the edge? I mean, there's some, I don't know, elements like resistors and stuff. There's the electric current. What is the... And the electric current has to do with speed, right? With the change of charge.
Yes.
The change of... time change of the charge. And the same is here, because now this is... The edge is our joint variable. For example, double loop joint is an angle, translation joint is a displacement. It's the same. So our velocity, exactly. So our current would be the velocity, right? So it's the same. And in the end, of course, when you have a closed loop, the velocities of all the joints there should be zero, because otherwise it wouldn't be closed, right? Okay. Long story short, we can actually have different loops. Okay. So we can have this one, for example. They're independent. You can also move this one here, and I don't know. I guess this is it. So the thing is, the number of loops of independent fundamental cycles, they call it, is clear, is unique. The fundamental cycles themselves not. You might change them. So, okay, wonderful. Yeah. Then we have different topologies, like tree topologies. So this was apparently a closed loop mechanism. And the topology graph had a closed loop. Now go back to this to the human body model, or let's say the humanoid model. So let's say the hip, for example, is, you can also have the feet, but anyway, normally the hip is the one is the starting point, so to say, right? And that I don't know, maybe you swap it upside down, and so because this is called the tree structure, because it looks like a tree. There's one root, and then everything emanates from there. And it's the same here. So I don't know how to model it. And there are different models. There are different, even high fidelity models for human bodies. But the simple model is that if the hip is, for example, the hip joint is just a regular joint plus a universal joint, and the knee joint is a regular joint again, which is not true, of course, because you can also do like a bit of this, and so on and so on. Anyway, so you can have as many as you want. Anyway, and then your number then it looks like this. So the hip is number one, and then you number then as you like. And in this case, it's not fixed to the ground, hopefully, right? Because you're not fixed to the ground. In particular, the hip is fixed to the ground. That means that your graph would have, and this doesn't exist, this doesn't line. So essentially, you have the humanoid graph, and then there's this kind of isolated node, which is just the ground, because the universe floating around. Right? Okay, good. What do I have to say? I don't know. What do I have to say? Yeah, so anyway, so and then the graph looks of course different, and same is for a grounded, for example, one. I mean, this is absolute just nonsense. I mean, this is just an example. It's just join, 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 and then it looks like this. So, but the important point here is that we have a kinematic topological tree structure. What's the time?
Till 137.
Wonderful. Yeah. So what is it there? Ah, yeah. So it looks like a tree, and it's a tree structure. When you do your programming, at one point when we look into the kinematics, you will have to say which body comes after what body. In the sense that I would like to, for example, compute. Yeah, let's say here. I would like to compute the motion of body 1, for example, right? As a consequence of joint 1 rotation. Somehow you can do this, right? So this apparently, I mean, this motion, this joint influences that body motion. Okay. Body 2 motion is influenced by this joint, and that's it. So what I would like to say is that at some point you will have to say which link and which body and which joint comes before another joint in order to actually compute the kinematics. Now, if you have a closed loop system, for example, yeah, this one, for example, that's not easy. I mean, no, it's not even not easy. It's not possible, right? Because what's the predecessor? What's the successor here? It's not easy to say, and actually, it's not possible to say. But what you have to do is to introduce this kind of tree structure, even for the closed loop system. And that, for example, goes like this. So let's again use this example here of our PKM, our the moving platform connected to the ground by 3 links. That was the topological graph, and I would like to introduce a tree structure in this. And that's again from graph theory. For any tree, for any graph, there is a spanning tree, right? A spanning tree is just so what's a spanning tree? So let's say we have a graph. You get the spanning tree by cutting off some edges, and you cut so often as you remove them, and you remove as many or as long as you have a graph that has no loops, but comprises all the vertices, right? So I cut this one. Okay, the vertices of course are all in there, but I still have a loop, which would be this one. Okay. Then I cut this one. So then I have all vertices and no loops. If I would cut further, like this one, then I would lose some of the nodes, vertices. So, and that's clear. And so anyway, there is a unique spanning tree for any graph, and that's it, because now you can actually talk about the unique predecessor. You know exactly which link or joint comes before another joint. So let's say I don't know, number 3, for example, it's absolutely clear which joints and bodies are coming before as predecessor of body 3. Because a body and a joint is a predecessor if it is actually in the path to the ground. So whenever you go from this, because there's a unique path to the root of the tree. Anyway, it's always unique. And any joint or body that comes, or vertex or node, vertex or edge, that comes, that is in this path is a predecessor. And the direct predecessor is just the one that comes after. Okay, I guess this is not so. Okay. Yes, and for if you really want to go into programming, then you need to introduce a directed tree, and that's okay. Yeah, that's not so much interesting for us. Yeah, and then of course it looks differently for different systems. That was actually the topological graph for this metamorphic hand. Again, maybe here you see it better. You have the 4 bar system. So you have the 1, 2, 3, 4, 5 temperature. No, 1, 2, sorry, 1, 2, 3, 4, 5 revolutors, because the edges are the joints, connecting the links that make the 5-bar system. So, I don't know, link number 1 is this one probably, then this one. That's not a nice picture. Anyway, and then come the finger, and then that's it. So so this is a kind of a mixed system, right? Because you have, of course, open kinematic chain here, and then you have the closed loop system here, and then of course, if you, there's one single loop, and then of course you can open this. And the same goes with this mechanism. And you see, for the PKM, there's always a nice structure, and this structure is what we're going to employ for the modeling of the PKM, because there's a whole theory, of course, for modeling closed loop systems, general closed loop systems, and that's a bit of mind-boggling. It's just not that easy. But for the PKM, we will have a very, let's say, an easier approach. And this approach exploits actually this very special topology, because it's always like that you have the platform connected by the kinematic chains to the ground. And maybe intuitively it's already clear that you can somehow treat all these chains independent, separately, and then somehow combine them. So this is going to be the main idea. Yeah.
Can you give 5 or 10 minutes for the different?
Yeah, sure. Yeah, I was actually about saying because we are actually almost at the end, because this is another topic. Yeah. Any questions?
The one with the hand. This one. At the fourth joint, why are all the 4 fingers connected? Is it because these 3 fingers are interdependent on each other? Like we could have had 5 integration points.
Yeah. I really have to find a better picture. So essentially you have, so look at this, that's the palm actually, right? And the palm is split. So the palm is split into a 5-bar mechanism. And the question is, on which, so you see there are 2 fingers on this part of the palm. So this is the 5-bar mechanism. So we have 5 links, and 2 are, maybe 3. 1, 2, 3, 1, 2, 3, 4. I see 4, right? Not 5. Maybe this is the parked position, because there is one position where it's parked with only 4 fingers. Good point, yeah. I don't know. As far as I see, link number 4 has 2 fingers.
Ring finger and little finger, both are there. But in this picture, only till the ring finger.
There's
After that, there is no little finger.
Yeah, maybe there's.
In this image, the little finger is also included.
Yeah. I guess this is because they have this. This is why it's called a metamorphic hand, because you can actually, move the 5-bar so that you can actually lock one of the joints and it becomes a 4-bar again. It's kind of a fixed system. And then you only have 4 fingers, but I don't see where they get rid of the finger.
Because in the next image it is written. Let's go to the next image, sir. No, next, I think, here you see the little finger is there. But in the picture, in this picture, little finger is not there.
Yeah, that's the point. I don't know.
So if you will take till the ring finger, so the question is, why this ring finger and middle finger have the one joint?
Maybe I copied the wrong picture, because they are all here. I mean,
yes,
the thing is, they are all. Now you have the middle finger, the ring finger on this link. See, this is one link here. And apparently, I guess so. In the 5-finger hand, you have also the little finger here. I guess the picture might not think like. Yeah, but the good thing, this is the important thing, because the palm is a 5-bar mechanism. It can move, right? That means that the attachment points of the fingers, of the index finger and the thumb, they are moving. Index finger and thumb. Yeah. Some are moving, and these 3 are fixed to one part of the 5-bar.
So maybe they are interconnected.
I can check it out. I don't know.
No, sir. When we try to move this one, they usually move little.
Yeah, but that's the biology. Yeah.
Yes.
This is not. Yeah. Yeah, good question. Everybody's tired.